In this part of waves in space time, we will move on to describe another type of disturbance that propagates through the space-time manifold and is detected at the observer. And this particular aspect of the space-time disturbance, so it's not just space-time disturbance, it can be any kind of disturbance. For instance, if it is a disturbance that is created in light, guess one, is created in some scalar field, number two. In the strong interaction theory, if it exists, it is 3. If it is in the oscillation of space-time fabric, it is a gravitational wave that can bear the signature of what we are going to talk. So, what are we going to focus now on? It is a sort of disturbance that generally is directed in a particular orientation, and this is called polarization. In nature, on most occasions, the emitters emit electromagnetic signal. I am just being generic, that is composed of this directed vibration that can be random. In general, if we have a collection of emitters and this collection of emitters are not polarized or been made to orient themselves and their direction of emission same, each one of them emits radiation randomly. So, if we average out the average orientation, when we take into account the emission from all the objects, it becomes equal to 0. But there can be situations where it is not the same, either in the source there is a physical situation which has been created. For instance, if we have a bunch of charged particles and we have a magnetic field, then the charged particles moving in a magnetic field tend to orient themselves in such a way that their energy is minimized and they almost all rotate in the same direction if their charges are the same. And when they emit light, this light can be seen to have a direction of vibration which is biased towards a particular direction. In the figure that I have for you is one such picture, where the light starts from the right top corner. It is seen to be vibrating in a north south direction, and it is propagating till it encounters a magnetic field and ionized gas. We will be tempted to call this particular system a magnetized system if the energy of the magnetic field or energy stored in the form of the magnetic field and the same of the gas are almost equal to each other, and it propagates through that system, the light, and when it comes out, it is seen to have tilted a little. So, how do you find out how much has it tilted from where it started? So, we will take a situation when the light starts and there is nothing in the intervening region, and light comes and falls on the observer, and what we see is that the alignment of the beam or alignment of the vibration of the electromagnetic interaction of the interacting electromagnetic field is the same, and we know that this is, if we mark it, we know that this is the actual alignment of the beam of light. And after we introduce this particular system, then what you observe is that the direction of vibration of the electromagnetic disturbance makes an angle with the north south direction. And this angle is what we say is a rotation that the beam of light has undergone. Any medium that brings such effect to a light that is plane polarized is called optically active. In general, the tip of the electromagnetic vibration did not lie on a particular straight line. It may in general execute a complex curve, that is something usually called the polarization ellipse, that is executed by the tip of the electric field vectors or the magnetic field vectors of the electromagnetic disturbance. And this polarization ellipse can make any angle. What I mean in broader sense is this ellipsis, this major axis of the ellipse can make any angle with respect to the Cartesian coordinate system of the observer, and the angle that its major axis makes with the x axis is what is termed as the polarization angle of the beam. But recall that we have an ellipse. So, when you talk of this polarization ellipse, it should have some characteristics of the, or you should be able to describe it in terms of some properties of the ellipse. And that particular parameter that brings out the property of the ellipse or ellipticity of the ellipse is called angle of ellipticity, usually described by chi, and this is the angle that the line, if you join from the left most corner of the x axis or the major axis to the bottom most point of the minor axis, is what is known as the ellipticity angle. Now, these angles that we have talked about here, since they are also angles, and when you are looking at a source from a slanted direction or you are looking at a source straight, and whether you are moving or you are not moving, is going to affect these two angles that we call psi and chi respectively, are going to be affected because of its motion. And that is the geometrical part of it, if we accept. So, a Lorentz transformation or relativistic transformation between the two frames should be able to capture this geometric effect, apart from the fact that the underlying medium that we have in any case through which this disturbance is propagating or this disturbance is generated are also going to contribute to this, to the determination of these two numbers. So, if some of us are interested to model a particular medium or model a particular kind of intervening space through which the signal is propagating, or wants to draw some conclusion about a different kind of phenomena that can generate this polarization of light, will be bounded by the limitations of the corrections that we have, or the corrections that would come from the situations we have just talked about. So, this is another aspect that should be taken into account when we discuss or describe the propagation of disturbances, be it electromagnetic, be it gravitational, or a medium that is made up of strongly interacting matter, usually termed as a system of quark gluon plasma. Okay. So, before we actually go about the details of these discussions, it might not be a very bad idea to just recapitulate or use our imagination to discuss the properties of the variables those are used to measure these observables that we just have termed as the polarization angle or the ellipticity angle. You know, if you actually look at this figure, there are few things that is very suggestive. What are those? The first thing is if you decide to set chi to be equal to 0, then you see that this whole ellipse actually collapses onto a straight line, which is from northeast corner to the southwest corner. So, your elliptical polarization turns out to be a linear polarization. And the situation almost remains the same with two lines vibrating. If you take your chi to be equal to 90 degree, then you will see that this ellipse is actually stretched and stretched, and if you take the radius or the major axis to be infinity, it becomes just two straight lines. Those are vibrating and they are joined at infinity and coming back. The second situation is slightly disturbing, but in the first situation, the polarization angle that we have defined by psi need not get altered, it can remain the same. But this variation in the angle chi can take us from a elliptical polarization to linear polarization. Okay, that is the first thing. Now, we can begin describe the system either in terms of the coordinates, rectangular coordinates that set by x and y, and if we so desire, we can go to a new frame of reference that is discussed or described by the major axis of the ellipse and the minor axis of the ellipse. So, we essentially have two frames of reference. One is tilted with respect to the other. So, we can use laws of transformation to go from this x y coordinate system to this rotated coordinate system of the major axis, minor axis, and still describe the phenomena. Maybe it's little hard to work on, but it's a doable problem. And this doable problem, if you work out properly, then we will find out how the parameters in one particular frame of reference depends on the parameters on the other frame. And if we do that, we can connect this polarization angle psi with the variables those were determined in terms of x y coordinate or the angle chi that is defined in terms of the parameters of the elliptic coordinate system with each other. Okay. So, given the fact that we know the amplitudes of the two waves, those are vibrating in the x direction and the y direction, and the phase between these two waves, and the frequency of vibration, everything in this description can in principle be worked out. Okay. And this algebraic description that I have just talked about can be captured in terms of new variables. Those are called Stokes parameters in terms of a physicist Stokes, and by the use of a matrix that is usually defined as a coherency matrix of the disturbing waves. So, if we know how these elements of this coherency matrix actually depend on the underlying coordinate transformation or Lorentz transformation, we can immediately estimate the changes that this geometric transformation would cause to the spectropolarimetric variables. We will come to this issue as time passes. So, we will come back and revisit this issue again in some detail as we progress. Thank you.